We finally arrived at our last chapter of the semester, chapter 11, and it is a big chapter. We're going to see a lot of addition reactions to pi bonds, both alkenes and alkynes. So one of the things that if you haven't done so already, you really need to start thinking about organizing reactions. I've put in place some templates, sheets for you for reactions, for mechanisms, and we're going to be looking at a lot of reactions and we're going to be looking at a lot of mechanisms. And the key for this particular chapter, so that you don't get overwhelmed, is look for patterns, recognize patterns. If you understand the mechanism of addition reactions, then things kind of fall into place and you don't really have to do a lot of memorization. You just have to think about how things are going to react with one another. And so that's certainly the key to being successful in organic chemistry, is to recognize how things react with one another. We're going to start off this chapter then thinking about the electrophilic addition of X2, or a halogen, which we call halogenation. We're going to see that an alkene will react with bromine, or it'll react with chlorine to yield what's called a vicinal dihalide. A vicinal dihalide. So, kind of a generic reaction is we take an alkene, we react it with a halogen, could be bromine, could be chlorine, and you get the addition of bromine across the double bond. So we've seen addition of HX across the double bond, we've seen the addition of HOH across the double bond, and now we're seeing the addition of BR, or XX across the double bond. And these type of products are called vicinal dihalides. So this is a vicinal dibromide. Now notice I don't mention fluorine or iodine, and the reason for that's pretty simple, because fluorine is way too reactive. It tends to catch things on fire a lot, and iodine is way too unreactive, and so we generally don't use fluorine or iodine to undergo halogenation reactions, only chlorine and bromine. Now, in terms of the mechanism of this reaction, it's a little bit more complicated than simple addition of HBr or HCl. Here we have, when we were adding HBr or HCl, the hydrogen didn't have any non-bonding pair of electrons. But when we're adding a halogen, the halogen has a pair of non-bonding electrons. And what that does is we can donate a pair of those electrons to the olefin carbon. Now the reason for this is because we know that carbocations are unstable. So if I have an atom that is in essence an electrophile, but it has a pair of non-bonding electrons to it, it can help to stabilize through resonance any charge built up on the carbon. And of course, the final step is the breaking of that chlorine-chlorine bond. So this is what the result looks like. And this is, we have this carbon-chlorine three-membered ring, and of course we also get chloride as the byproduct, although chloride is a nucleophile. So this is called a chloronium ion. So chlorine has a bond to each carbon. It has two non-bonding pair of electrons, and it has a positive charge to it. And that chloronium ion, like I said, is going to be more stable than any carbocation. Why? Because all of the atoms have an octet of electrons around them. So again, when we are adding HX, we couldn't stabilize anything because the hydrogen can't have any more than two electrons around it. But now with a halogen, we can stabilize it. So the next step is the chloride then undergoes a simple substitution reaction, SN2 type of substitution reaction. So it attacks one of the carbons and displaces that carbon-chlorine bond. And we end up getting two chlorines adding across the double bond a vicinal dichloride in this particular case, in general a vicinal dihalide. So why do we know that the chloronium ion doesn't form? Well, we've already talked about one reaction in which the mechanism was slightly different than the carbocation formation, and that is hydroboration, right? So in hydroboration, we know that we don't form a carbocation because there's no rearrangement. Well, guess what? One of the reasons we know the halonium ion forms is because there is no rearrangement. So these are clues that that we have to think about the mechanism. This is one of the clues, and we're going to see another reason for us thinking about the mechanism as a chloronium ion in just a little bit. But just to make sure that you understand what I'm talking about, let's assume that that a carbocation formed, right? So why do I say a carbocation isn't forming? Well, let's say that I take this alkene here, so 3,3-dimethyl-1-butene, and I react it with bromine, and I get just a simple electrophilic addition, right? The alkene attacks the bromine, and I get the bromine-bromine bond breaking. And what would I form? Well, I would form a carbocation, right? And now look at this carbocation. Well, what have I talked about? When you have a carbocation that forms, you always have to think about rearrangements because they often occur. And if this carbocation were forming a secondary carbocation with a quaternary carbon, I would definitely get a methyl shift occurring, right? And so I would certainly predict that I would get this carbocation, which is more stable, a tertiary carbocation, more stable than a secondary carbocation. And of course, bromide would then attack that, and I would definitely not be making a vicinal dibromide. I know this reaction doesn't occur at all, and therefore there can't be any carbocation that forms from this reaction. Another reason that leads us to think about the bromonium ion or the halonium ion forming deals with stereochemistry. So if I think about the reaction of cyclohexene reacting with bromine, so the pi electrons add to bromine, the non-bonding electrons go back to the alkene, the bromine-bromine bond breaks. I form now a bromonium ion. Well, that bromonium ion, if I'm assuming that the carbons are in the plane of the board, the bromonium ion has to be coming out at me, or it has to be going behind me, correct? Of course, they're the same. If I wasn't forming the bromonium ion, and instead I was forming a carbocation, so bromine simply adds to one of the carbons, the other carbon becomes a carbocation. Now the bromide that comes in could attack either side, either face of that carbocation, and I would get a mixture of cis and trans 1,2-dibromocyclohexane. And that's not what happens at all. So I know that the mechanism has to be that my bromonium ion forms, the bromide then attacks the bromonium ion, and it attacks in an SN2 manner. So why is that important? Well, because in an SN2 substitution, we know we get inversion of configuration. So the bromide has to attack from the opposite side. Why? Because that sigma star of the carbon bromonium ion, the correct orientation of that orbital is in the opposite direction. So the bromide has to be coming in from the opposite direction, and I end up getting trans 1,2-dibromocyclohexane. That's the only product that I get when I take and I halogenate cyclohexene, right? So this, again, reinforces our idea of the mechanism being the formation of a halonium ion or a bromonium ion or a chloronium ion instead of forming a carbocation. So a few examples, I can take 2 pentene and I can react it with chlorine and I get 2,3-dichloropentane. And depending on the stereochemistry of 2-pentene, if I had trans 2-pentene, I would get a racemic mixture of 2 enantiomers. If I had a mixture of trans and cis, I would get all 4 possible stereoisomers of this reaction. Right? Here I have an example where I have a benzene ring with an alkene. So one of the things that you have to always remember is benzene does not behave like an alkene. Even though we draw those double bonds, it doesn't behave like an alkene. We're going to get into that chemistry in the second semester, but suffice to say, at this stage, when you see benzene or other aromatic hydrocarbons, they do not undergo addition reactions. And so, if I were simply to look at this molecule, I have to recognize there's the alkene is present, bromine in carbon tetrachloride. Carbon tetrachloride is a nonpolar solvent. It's very good for halogenations simply because the halogens will dissolve in it. And I get the formation of my vicinal dibromide. Again, depending on the stereochemistry of the alkene, if I have, the trans alkene, I get a racemic mixture of the 2 enantiomers. If I had cis, again, racemic mixture of 2 enantiomers. If I had cis and trans, then I'd get all 4 diastereomers of this product. And so here now I have 1-methylcyclopentene. And again, I can now start thinking about stereospecificity because obviously the stereochemistry of the alkene is fixed, and therefore if I react this with bromine, I'm going to get anti-addition. It's called anti-addition because the bromines are adding on opposite sides of one another. So syn addition when they add on the same side, anti-addition when they add on opposite sides of one another, and I get this product plus it's an enantiomer as well, right? Now, one of the little twists is that if instead of using a nonpolar solvent like carbon tetrachloride, I used a polar protic solvent, I get new products that form from this reaction. What's happening is, let's say I have cis-2-butene, and I react it with chlorine, but now instead of using carbon tetrachloride, I use water. Well, what happens in this reaction? Well, let's think about the both the nucleophile and the stereochemistry of this reaction. So the first step is obviously the pi electrons attack the chlorine. The non-bonding pair of electrons on chlorine go back to the pi system, and the chlorine-chlorine bond breaks. I form now my chloronium ion, and the stereochemistry is such that if I started with cis-2-butene, the 2 methyl groups would be on the same side. The 2 hydrogens would be on the same side as one another. Now, so that's the stereochemistry of the chloronium ion. Typically, what we would see is now chloride attacking one of those carbons. But when you have water present, water is a nucleophile as well, and it overwhelms the chloride because there's lots of water molecules present. And therefore the nucleophile becomes the water molecule, it becomes the polar protic solvent. Now notice in this particular case then, the polar protic solvent can attack either one of the carbons. So it can attack the carbon on the right, or it could attack the carbon on the left, displacing that carbon-chlorine bond. Now, if we think about each one kind of separately, what's going to take place there? Um, well, let's look at the arrows on the right-hand side. So let's assume the water attacks the carbon on the right. Again, SN2 substitution, we get inversion of configuration at that carbon. The carbon on the left then doesn't change. It still has everything attached to it the way that it was, right? And so we can draw this species right here, and we're going to get an oxonium ion forming because, you know, we can't just magically remove a hydrogen there. So you form the oxonium ion, and notice the carbon on the right underwent an inversion of configuration. So the hydrogen and the methyl group are pushed away from the nucleophile. The hydrogen's still coming out at me, the methyl group's still going behind me, but they're being pushed away from the nucleophile. Now, if I think about the attack on the carbon on the left-hand side, again, it's going to undergo inversion. The carbon on the right stays the same. I still end up with an oxonium ion. And so I get a mixture, a racemic mixture of the two enantiomers. These are enantiomers of one another. And now notice that when I take you know, my last step is certainly I have to deprotonate it. So I'm just drawing these oxonium ions again. You don't necessarily have to do that if you're writing these down. So here are my oxonium ions, and I simply deprotonate them. How am I going to deprotonate them? You should know that by now. Water is my solvent, and I can simply use water to deprotonate them. So I end up with these two structures here. This is one of them, and this is the other one. And so you see for this particular, these are enantiomers of one another, so I would get a racemic mixture of enantiomers. Now, if I look at the product, these are what are referred to as vicinal halohydrins. Vicinal halohydrins. So I've added a halogen and I've also hydrated it at the same time. That's where you get the halohydrins forming on carbons that are attached to one another. Now, one of the cool little features about running the reactions, a halogenation in a polar protic solvent, is now we can think also about regioselectivity. When you're simply halogenating an alkene, the two halogens are the same, and therefore you can't really tell any specific regioselectivity in the reaction. Well, now we can, because if I take, let's say, 2-methyl-1-propene and I react it with bromine and water, the same thing's going to happen. I'm going to form my bromonium ion, right? So here I form my bromonium ion. The pi electrons attack the bromine. The non-bonding electrons go back to the carbon, and my bromine-bromine bond breaks, right? I form my bromonium ion. And now notice what I have is I have a situation where water can attack one of either carbon. So what's going to happen? Am I going to get attack at both carbons, at which I get two different products, or am I going to get attack at only one of the carbons? Well, the way we have to think about this is we have to think about resonance of that bromonium intermediate. Now, certainly, this is going to be the most stable intermediate. The bromonium ion is the most stable intermediate. Why? Because all of the atoms have an octet of electrons. But we certainly can envision, you know, if I attack either one of these, you know, which one of them is going to occur? Well, again, thinking about resonance stabilization, I can envision two possible minor resonance contributors. I have one where, the middle one where I have a tertiary carbocation like nature, and one on the right-hand side where I have a primary carbocation-like nature. Well, obviously, the bromonium ions certainly going to be the major resonance contributor. It's the most stable, but that tertiary carbocation nature is certainly going to be more stable than a primary carbocation type nature. And therefore, when water goes into attack, it's going to attack the carbon on the left and not the carbon on the right. And therefore, we get regioselectivity. Notice there is no carbocation that forms, right? Still the bromonium ion forms, but because of the partial positive nature of the more substituted carbon, we see that water simply attacks the more substituted carbon. So again, understanding the kind of nature uh, of um, of carbocation stability, even when there isn't carbocations around, right? This partial carbocation stability can help in explaining the regioselectivity of reactions. So again, let's look at a few examples. Here I have 3-methyl-1-butene reacting with bromine, now in the presence of methanol. So if I have methanol present, not water, I'm not going to form an alcohol or a halohydrin. When I have methanol present as a nucleophile, I form ethers. Yes, ethers. I do not form alcohols. So please don't make that mistake, right? Common mistake is you say, oh, it's a polar protic solvent, OH. I'm going to add OH. Nope, you're going to add OCH3. So you end up getting a vicinal halo ether, when you use an alcohol as a solvent instead of water. So water, you make a vicinal halohydrin, and alcohols, you make vicinal halo ethers, right? Now I can, so if I take 1-methyl cyclohexene, treat it with chlorine in the presence of water, now I have stereochemistry to contend with. I also have regiochemistry to contend with. So stereochemically, the water is going to add anti to the chlorine, right, because SN2 substitution. So I get anti-addition. The OH and the Cl are on opposite sides of one another. In terms of regiochemistry, the water always attacks the more substituted carbon, and therefore my product would look like this. So OH and Cl are anti to one another. OH is a dash, Cl is a wedge. And the OH is added to the carbon that is more substituted. Now notice I could have reversed this and said that OH is a wedge and Cl is a dash, and so obviously I can also get the enantiomer of this product as well, right? So let's take a look at methylene cyclopentane reacting with bromine in the presence of methanol. So again, we have to think about methanol. Methanol is going to make a methyl ether. It's going to attack the more substituted carbon, and therefore my product looks like this, right? So all these little things that we have to think about, but if we understand the mechanism, and we can kind of think about the mechanism. The way I do these types of problems is I'm thinking about the mechanism in my head. I'm not necessarily writing it down, but I'm certainly thinking about, okay, what's going to take place? Sometimes you might want to start off drawing out the mechanism and get to a stage where you can predict the product. So you definitely need to get to a stage where you can predict product formation without having to write out the mechanism. But certainly, having that mechanism in the back of your head, what's happening? I'm forming a bromonium ion. Methanol is coming in and attacking that bromonium ion. What carbon is the methanol going to attack? It's going to attack the more substituted carbon. Do I have to worry about the stereochemistry of this reaction? Do I have to worry about the chemistry of this reaction. All these things are taking place in this one little reaction. So, there's a lot to kind of keep track of. Again, understanding the mechanism will help you to keep track of those things. So the last thing is thinking about halogenation of alkynes. Remember I said we're going to be looking at addition reactions of pi bonds. So there's alkenes, there's also alkynes. And alkynes will also undergo a lot of addition reactions similar to alkenes. One of those reactions is halogenation. And so we can certainly halogenate an alkyne, and it gives a mixture of products oftentimes. Sometimes we get vicinal dihalides, sometimes we actually get tetrahalides. So for example, if I take one propyne and I react it with chlorine, an excess amount of chlorine at 65 degrees, I get two major products. So I get 1,2-dichloropropene. I also get 1,1,2,2-tetrachloropropane. And the yields kind of vary. So usually the vicinal, this is a vicinal dihalide, right, and yields of 15 to 20%, but the tetrahalide is actually the major product, 60 to 65% of the tetrahalide. And so why am I showing, usually we get the tetrahalide, that's kind of the major product, but I want to show you that you get this trans dihalide, because that trans dihalide does suggest that a chloronium ion intermediate is being formed. However, the mechanism for halogenation of alkynes isn't well understood. So we get a glimpse of thinking about a chloronium ion, but when we think about the geometry of that chloronium ion, things get a little bit weird, because we have this linear structure with a halogen kind of hovering over the pi system. And so it's actually a little bit more difficult than the addition of a halogen to an alkene. The other thing is because of that geometry, alkynes are much less reactive than alkenes when it comes to halogenation. So alkenes can be halogenated in the presence of alkynes. For example, if I take this particular structure here, so this is an ene-ine, I have an alkene and an alkyne present, and if I react it with one equivalent of bromine in carbon tet, keeping the temperature low, I can actually halogenate an alkene, getting a vicinal dihalide, without touching the alkyne. But in general, alkynes will react typically at a little bit higher temperatures, typically in excess halogen, such that we get tetrahalides forming. And so you see a lot of those types of reactions.